Now approaching to the end of our conference, let me present to you our last, but of course not least speaker. Actually, I tried to find some interesting fact about her, but I failed because I couldn't pick the only one fact. I just want to say that I'm already excited about our last presentation. Meet Tatiana Al Chueyr Martins, Senior Data Engineer at BBC. She will tell us about scaling machine learning scaling machine learning workflows with Apache Beam. Welcome. Hello, Tatiana. Can you hear us?
Hello, hi Alex, I can. Can you hear me?
It's great. Yeah, we hear you. How are you? Excuse me for our
I'm
technical
fine.
issues. Sorry for this delay.
No, it's perfect. It's perfect. Thank you so
Great.
much for the opportunity to be with you at MultiNixConf.
That's great. I think I can't delay it anymore, so you can start your presentation.
Okay,
Good luck.
so thank you very much. Dobre rodzina, dobre dzień. So a bit about me. I'm Brazilian, living in London since 2014. I'm a senior data engineer at the BBC. I graduated as a computer engineer, and I'm really passionate about software development for over 16 years. I already worked for the public and the private sector and in multiple areas. I really love the Ukrainian community and the country itself. My first time to Ukraine was last year when I had the chance of going to Kharkiv for 3 days. There, myself and my daughter Amanda were keynote speakers at Octopuscon. I also lectured at Kharkiv National University of Radio Electronics. I was really, really impressed with both the conference organization and the community, how strong the tech community is. And we even had some dolphin therapy at the Nemo Dolphinarium. It was really brilliant, and I hope to be there many more times. A bit about the BBC. So, BBC stands for British Broadcasting Corporation. It was founded in 1922. In the UK, the BBC has no advertisements, and who pays for us are residents who want to watch us. We are independent. We try to be as impartial as possible and honest. The audiences are at the heart of everything we do, and we aim to inform, educate, and entertain the audience in this order. The BBC reaches 91% of the UK population, and we reach 426 million global audience weekly. That's more or less 10 times the Ukrainian population. Every day, the BBC produces around 2,000 pieces of content. However, there are a limited number of available slots to occupy. So there is always a challenge of what is going to our websites? How are we going to surface this on the TV? And that's when my team was created. So I work for the Data Lab team, and our objective is to be able to apply machine learning to improve the experience of the audiences, always prioritizing the needs of individuals and society over corporations and states. And another mission of our team is to allow anyone within the organization to build and scale machine learning while still respecting the editorial values of the organization. This is our team before COVID, and this is part of our team post-COVID. So, yes, I can't wait to be back to the office. We're quite a remote team, but it's always good to see people face to face. So, this presentation is about a challenge we had around a year ago. So the BBC has several applications. One of them is called BBC Sounds, and it wanted to improve the overall experience. So it hired an external provider to build a recommendation engine to give personalized experience. So this recommended for you rail. Based on our A/B tests, the audience liked it. There was an improvement of over 10% over time. So the question was, could we replace this external provider, giving a better overall experience to the users while having the knowledge and be able to customize it so we can serve even better our audiences? And that's when we accepted the challenge. So we decided building a recommendation engine for this product. And we had a few approaches we could be using. So one of the approaches would be to have content-based recommendations, where we recommend things similar to what this specific user watched in the past, being one of the drawbacks of this strategy, the fact that sometimes the recommendations are quite repetitive. Another strategy we had was using collaborative filtering. So to assemble all, to analyze as a whole the experience of all users, to try to identify similar users and cross-recommend things that similar users watched, but you didn't. This approach has the drawback that usually if there are new fresh items, so those 2,000 new items we publish every day, they wouldn't be surfaced through the recommendations. So our decision was to adopt a hybrid approach called factorization machine, which uses both strategies into one. So we had to build a machine learning workflow. We had historical data. With the historical data, we were able to train a model. We created some artifacts related to this model, and then we had to then predict recommendations for the users using the new fresh available data. And then we give the users, please have a look at these items. We think you might enjoy this content. So before we advanced any longer, we didn't want to spend months building pipelines without knowing if the factorization machine algorithm was promising or not to the end users. So within a month or so, we collected lots of data, the user activity data, the program metadata data, and we compared the existing factorization machine library. We analyzed some implementations in Python, and within our analysis, we had among them LightFM, XFactLearn, I think, and another one was TensorFlow. And by the time LightFM met the requirements of our data scientists, so we created some scripts to quickly train and predict recommendations for users, and we created a qualitative experiment tool, so we could get a group of users who would then try out those tools and see if the recommendations looked similar or better than the existing ones from the external provider. So we built this interface. The first list was there were two lists with recommendations similar to what would be displayed in the product app, and the users had to pick either A or B. We would randomly add our own recommendations or the existing external provider, so the people evaluating wouldn't be biased. They didn't know which was which. And there were around 30 test users who evaluated, and they gave some qualitative feedback saying, look, I prefer this because it has more fresh content, or because it's more similar to things I've seen in the past. Within this qualitative test, over 60% of the users preferred our recommender than the existing one. So the results were really, really promising. We did a few iterations of this until we were convinced this was a strategy worth implementing. So then came productionizing this. Something that many people don't realize is that sometimes there is this very sexy thing about machine learning, but most times, most of the work is engineering. So if you see this diagram, this was copied from a presentation of the Googler. I added the link there, there's the credit. And it basically shows that sort of red part in the middle is the shiny machine learning bit, and all the rest are engineering tasks. So to collect data, transform, extract features, verify the data, manage resources, analyze tools, have tools to manage and orchestrate those workflows, serving, and then monitoring. So there is plenty to do, which is mostly engineering or DevOps. In this particular case, we had two sources of input, so the user activity data and the content metadata, in that case programs. Then we had to train the model, and we had to predict recommendations, and then we would output recommendations to the users. A few of those steps added to this, we also had 2 additional steps, which were business rules. So our editorial team is really keen on us having several things implemented. So to make sure we only show recent content, well, not necessarily recent, but to boost recent content, to only show available content. They wanted to exclude some of our channels, and they also want us to avoid recommending items the user already watched. If the user was watching something which was part of a series, to make sure that we were surfacing the next episode which would make sense for that user. So some of the things in this diagram were quite clear, made sense to be in a workflow. So the user activity ingest, the content metadata ingest, the training of the model itself. But what about the application of rules and the calculation of the recommendations itself? So we had 2 possible approaches. There would be other approaches, but these were the 2 we focused. One of the strategies would be to surface the model live through a Python API using Scenic. In this case, the API would be interacting with the user activity and content metadata, loading the model in memory, predicting things on the fly, and applying rules. And the other strategy would be workflows do all the hard work. We would predict recommendations for all users, and we would save those recommendations and cache them. Our goal was to have the API being able to serve at least 1,500 requests per second, with a 95 percentile of the requests taking less than 60 milliseconds. So we implemented both strategies and we run load tests. So these are some of the numbers. With the on-the-fly strategy where we had the live model, if we had 50 concurrent requests, so all this considering we were running in Docker and Kubernetes, inside the C2 standard 8 machine, it has 7 vCPU cores, 15 gigabytes of RAM. Those were the configuration in our Kubernetes deployment, and only 1 replica of the API. So we didn't want to validate auto-scaling. We just wanted to see how much a single pod running this API would be able to surface. So initially we run in these 2 first columns, load tests with only 50 users per second. And as you can see, the loading the model in memory, as expected due to the Python global interpreter locker, wasn't necessarily efficient, because if we wanted to make it efficient, we would probably need to have a core available for each thread predicting. And in this case, we only had 7 cores. So we only were able to answer more or less 7 requests concurrently. So when we tried to add a load of 50 users, only 63% of the requests were successful, and the latency was almost a second per request, quite above our goal. Whereas when we added the pre-computed recommendations to Redis, and we made our API be just an I/O bound, making requests to the Redis cache, we were able to surface all the requests successfully when we had 50 requests, and P95 of them would take 3 milliseconds. And when we increased the load to 1,500 requests, again, using a single pod, we managed to achieve our goal. So we managed to get almost 60 milliseconds for P95 of the requests. So based on this, the on-the-fly strategy didn't solve our issue. So our workflows would need to contain most of these steps. So to ingest the data, to train the model, to apply rules, and to pre-compute recommendations. So in order to orchestrate our workflow, we wanted to be able to schedule jobs, to retry executing a task if it failed. We also wanted to be able to have all these blocks connected in a way, if this worked, to follow up on the next tasks, to have some monitoring and logs, to be able to, using Python, define the behavior of our workflows, and also to be able to have automated tests. This is an example of one of the pipelines we built. We chose the tool Apache Airflow. And it worked quite well. So not only we used Apache Airflow, but since we use Google Cloud, we adopted the Cloud Composer, which is a managed version of Airflow, and that saved us quite some time. Composer also offers some monitoring, so our criteria was sort of solved. Initially, we thought that we would be able to use plain Python operators in most of the steps of our pipelines. Since Airflow orchestrates so well things, we were optimistic we would be able to limit our toolset to using Airflow. However, we noticed, based on experience, that Airflow wasn't necessarily good for processing data-intensive tasks within the Airflow workers itself. It was designed to be an orchestrator, not an executor. So, as an example, this pipeline changes program metadata. When you look at the times, so each of these boxes is a task, and this diagram in Airflow illustrates how long the tasks are taking overruns. So you can see 100 executions of that DAG, of that workflow, and you can see there are some spikes. So depending on the amount of program metadata which was added, we had spikes which would take 3 hours to process the data, whereas in average we would have around 20 minutes or much less. So this sort of time was unacceptable for our use case. So to take 3 hours was not acceptable for two reasons. So one of the reasons was the time. We want to have speed in processing our workflows. The second reason was when a worker was processing this, it wasn't getting jobs Airflow needed to delegate and advance on other tasks. So it affected potentially other DAGs and other workflows we had to run. Added to this, an example, for us to be able to pre-compute recommendations. These were some of the times we estimated it would take. So if we were to run in a VM, predict recommendations for 10,000 users, using an instance with 30 vCPU and 120 gigabytes of RAM, that would take us around 2 hours. So this made us a bit concerned because Airflow by itself wouldn't necessarily allow us to parallelize this load and pre-compute recommendations and run other steps of our pipeline efficiently. So imagine if it took 2 hours to predict recommendations for 10,000 users, it would take ages for 5 million users, 500 more than that. And we didn't have that time. So that made us delegating processing to other components within the Google Cloud environment. Some of the options we considered were, if we had to scale vertically, we could use either compute engine, virtual machine operators, which would spin up a VM, run the tasks there, or we could do a similar strategy using Kubernetes. And for tasks which could be split into chunks, we could then use either Dataflow, or which runs Apache Beam, or Dataproc, which allows us to run Spark. Given the knowledge of the team and the experience, we ended up using the Kubernetes pod operator for scaling vertically. So that's how we ended up training the model. We already had a cluster for serving, so we just spinned up some additional node pool there for the workflows. And regarding the splitting of the tasks and parallelizing the processing, we used Dataflow because it allows us to run things locally and remotely using Python. And this was really, really convenient. So a bit about Apache Beam. Apache Beam, which is what Dataflow implements. Apache Beam is a unified programming model designed to provide efficient, portable data processing pipelines. You can write in multiple languages. It currently offers support to Python, Java, Go. It supports both batch processing and stream processing. And you can have lots of different runners. So if you were on-premise, you could have your Spark cluster running those tasks. You can run direct runners in your local computer, or in Google Cloud, you have data flow runners. So the overall view of how a data flow job works is you have some data input, you transform that data, and then you output some data. So those are some of the concepts of how Beam works. And in most of these steps, you can process things in parallel. So let's say you have Porky files, which are parallelized by nature, or let's say you have a task where you're trying to apply transformations to chunks of the data. All those things can be parallelized. And who is implementing the pipeline doesn't necessarily need to worry about how that will be parallelized. So an example from the Beam website, you define a Beam pipeline. In this case, it's creating some data sets. You could be reading this from multiple sources, from databases, from files, from object stores like GCS or S3. Then in this case, it's reading two data sources and it's merging them. So you get those two sources, you merge, and then you print them. So it prints this. And as you can see here, it doesn't say anything about how many machines, what machine types we should be using, or how to parallelize them. Beam tries to abstract those concepts so anyone engineering from an engineering background, data science or whatever, would be able to benefit from parallel processing without much effort. So this is how a Beam pipeline looks like. This is one of our production pipelines. So we, in this case, we're reading two data sources, merging documents, parsing, and outputting the file. You have visibility. Initially, the workers scale up. You process the task. They scale down. And you have visibility of how much CPU, memory, etc. is done. So data flow is sort of serverless from the perspective you don't need to manage the resources themselves. But it's still, if you want to understand what is going and best use the resources, it is useful if you understand what is going on inside of each, but it's not mandatory. An example of how efficient data flow can be, this was one of our first pipelines. It allowed us to process 40 million items, around 27 gigabytes, in 1 minute using 10 default workers. So opposed to the issues we were having with Airflow, when we tried to process things within Airflow workers, it looked really, really promising. So then we adapted some of our workflows to replace native Python operators, Airflow operators by Apache Beam operators. In some cases, the gain performance was 90%, and that was just because we limited the amount of workers. In many cases, it could be better or worse, depending on, not worse, but the gain would depend on how many workers we assign to data flow. And data flow also allowed us to pre-compute recommendations to millions and millions of users. So this is our pipeline which we use to pre-compute recommendations and apply business rules as well. Now, even though Beam and data flow gave us lots and lots of gains, there were some lessons we learned with these. And I would like to share about a bit of this with you. So before that, I made this quiz time. I don't know if this will work really well. It's the first time I'm trying this, but since you guys have been watching this presentation for so long, I just thought it was a chance for you to try to interact a bit and not only watch. So there is this link here, which was supposed to be a short link, but it's quite long. There is this QR code which you could scan. And if nothing works, you can also check my Twitter account. So there is my Twitter handle on the bottom. And hopefully, if you go to that, you would be able to see this data flow quiz. So the first question, there are two interesting scenarios which we found about with experience using Airflow. So the first of them was we had a pipeline, which was relatively simple. And we attempted to run that pipeline using two different machine types, because when you run data flow jobs, you can specify the machine type. So in one of the cases, we use a machine type which had a single vCPU. The other case was a machine type which had 4 vCPU. In one of these pipelines, it took a particular transformation, this enrich consumed items took the equivalent to 2 days of processing. Whereas in the other one, it took the equivalent of 5 hours processing time. And this processing time, it's the aggregation of the effort all the workers had. In practice, it was just a few minutes from a user perspective, but you can see there was a massive difference of 2 days versus 5 hours from a computation perspective of what went inside data flow. And we were quite surprised about this. So this first question would be, which do you think was which pipeline, which used what type of instance type? And it's okay if you don't have any idea. The second scenario, we wanted to understand how good data flow would be for some of our use cases. And one of the use cases was just to read 130 Parquet files, which in total had almost 10 gigabytes of RAM. And then we wanted to extract value from one column and to export that in new files. And we had 3 implementations. So one of them was a single-threaded PyArrow running in my computer or in a VM. The second was data flow auto-scaling up to 10 workers by itself. The other was using data flow, but fixing them out to 10 workers. And I would be curious, what do you think it performed better? So while you take your time, I would just continue with the presentation. So let's go back to present mode. So to be or not to be. So this is the second scenario I described in that survey. So we had this 130 Parquet files, which totalized almost 10 gigabytes of RAM. We just wanted to read one of the columns, extract the value, export to new files. We tried these 3 different implementations. Which was the most efficient vCPU, memory, and time-wise? Dun, dun, dun. So interesting enough, PyArrow was the one which was the fastest. We were able to process in 3 minutes, opposed to 12 and 7 minutes with data flow. It used less vCPU and used less memory. So I think the interesting lesson with this is, depending on the size of your data, if you're not processing terabytes of data, sometimes, depending on the task, simple tasks might be more efficient being run directly in Kubernetes pods or in VMs, and not necessarily data flow will be the answer to solve all the problems. Another thing which might sound surprising is that auto-scaling took longer than fixed workers. And many times when people are using managed services like Lambda and so on, sometimes there is this belief that those tools will do the best for us, but sometimes to actually know your data, know the characteristics of what you're processing, allow you to make choices which will be more efficient than if the hardware just tries to guess what will be better in every case. Human beings still play a role there. Another thing to keep in mind is the actual time for Beam to process things wasn't necessarily the 7 minutes, because there is a moment when Beam sets up VMs, it then processes things, and then it tears down VMs. And this time includes all those steps. So this might explain why a local execution with PyArrow might seem so much less than the data flow. So again, if you're processing jobs which are really quick, really tiny, perhaps data flow might not be the right tool for that. Then there is the problem I described in that poll, where we had the same exact code, the same pipeline, and for some reason, when we just changed the instance type, we went from 2 days of processing this particular task to 5 hours. Remembering that in practice, this pipeline was taking, I don't know, 7 minutes, but those are the steps. It is just the relative time that being believed it took allocated vCPU time for that across all workers. So in this particular case, it was quite drastic, the difference of processing time, and it's quite drastic, the difference we pay for them. So we were quite surprised that the worse machine type allowed us to run things more efficiently than the better machine type. And in this case, we opened a case with Google, the data flow team. They're still investigating what exactly went wrong there. We don't have an answer yet. But it does seem that whenever you have instances which have multiple cores, so you can see there was a single core here, there was 4 cores in this, being delegates multiple executors per VM. And then there is an overhead with this type of operation. So there is a likelihood there was some bug there that to process this particular task resulted in this delay. I hope to have the answer soon. I will be sharing Twitter when we find out. Some other problem we had with data flow was that sometimes we would receive this sort of cryptographic error message saying connection reset, depending on the type of job we were running. And this would particularly happen when we had memory intensive tasks, such as loading a machine learning model, which is 10 gigabytes of RAM, would occupy 10 gigabytes of RAM, and then trying to pre-compute recommendations. And what this connection reset error means is that the VMs which were running the Beam worker got killed, and then the orchestration of data flow with those VMs failed. And then data flow tries to delegate to new VMs that same job. But in this particular case, the problem was that we wanted to use 10 gigabytes of RAM for each task executing, and we were struggling finding the adequate machine type which would allow us to have the model loaded in memory. And whenever we had a machine type which had more than one vCPU, being tried to allocate 2 executors to that same machine, and then it would run out of memory because it was trying to load the model twice in the same machine. So let's say the model had required 10 gigabytes of RAM. When we tried to load it, it would be 20 gigabytes of RAM. The VM would get killed, and then we would get this connection reset error. By the time we had a few chats with Google, we posted a question in Stack Overflow, and some of the solutions would be to have a custom machine type with extended memory, so we could have the exact ratios we wanted based on being data flow executors inside each VM. The other option was to use shared memory feature from the latest version of Apache Beam. Another thing we've been learning is how to analyze the costs of the Beam pipelines. So these are some of our pipelines, a sample of them. And you can see that most of them, the costs were quite reasonable per month. Less than £100, having hundreds of executions and things per month. However, we did run into an issue where the first version of our Beam pipeline to predict recommendations was costing us $300 per execution. And that was pretty expensive. So the most expensive step was this predict, and this step required us to have a huge memory available per executor inside each VM. So some of the strategies we then used was to use the shared memory feature and also to split the pipelines. So we only need to have machine types which have lots of memory for this specific step, opposed to the whole pipeline. The other steps didn't need to have much memory. So that's my team, Data Lab Rocks. We try to update this website with information about what we're developing. Before we end the presentation, I'm curious if anyone replied our survey. Oh my God. So let's see. We had some people who did reply, 3 responses. Some of them didn't get quite right. One got right. So that's really cool. I hope this was replied before I showed the real responses. And here, so that's it for me. Duże Tobie dziękuję and boa stoi spasiba. Thank you very much.
Thank you very much, Tatiana, for your presentation. It was really great and interesting. First of all, let me present to you as to our other speakers, our mascot and our gift box. And because we're really lack of time, I think we can ask only one question. And the first lucky one who's got his question is the author of the question. What other technologies are good in this case that you described in your presentation? What if not Apache Beam?
I believe a Spark, PySpark would be the second next choice. And the drawback with Spark is that you have to have a Spark cluster. The good point of Spark is that you have full control of what's going on there. So you don't have to rely on these magic black boxes from Google, which will be processing things. You are able to configure exactly the instances. So more power, but more knowledge as well. I think PySpark would be the best option there to parallelize things. And as I mentioned, and if you're using Google Cloud, you can use Dataproc. Regarding vertical scale, if you weren't using Kubernetes, you can always delegate works to VMs or other things. So those would be alternatives to the problem.
Thank you. Yet another time, excuse me for our delay. Thank you for your attendance. It was a really great presentation. It was really interesting. We hope to see you next year and on our next conference. I think already offline in real life. Have a great time.
Thank you very much, Alex. Thank
Goodbye,
you. It was a pleasure participating. Thank you. Cheers. Bye. Congratulations to the organization. Bye.